Okay, so we're going to look at writing individual electrons, telling which orbital they're in based on their spin, based on their placement on the periodic table and their placement of electrons around the nucleus, all that kind of stuff. We're going to look at something called orbital notation. Okay, so when we're looking at orbital notation, it's typically drawn with some arrows, and we'll have a single line that identifies an orbital, and we label the orbital underneath. Okay, so here we've got our three of our first orbitals. We have a 1s orbital, a 2s orbital, and our 2p orbitals. Why do I have 3 different lines for 2p orbitals? What do you think, Alexis?
They have 6.
Yeah, the 2p orbitals can occupy 6 electrons, right? So that means each of these lines can only occupy 2 individual electrons. Okay, we're looking at our orbitals here, and we talked, remember the p orbitals have 3 different shapes, an x, a y, and a z, so that's why we have 3 different spots for electrons to go in the p orbitals. It can be on either of the 3 axes, px, py, pz, okay? But each of these lines represents an orbital for us, and how many electrons can go in each orbital? 2. We can have 2 electrons in each orbital, okay? So when we're looking at orbital notation and we have blank lines, that means that orbital doesn't contain any electrons. Okay, so right now we're not looking at any element because we don't have any electrons drawn. So an orbital containing 1 electron, we've got one single arrow. Okay, and we always label our orbital underneath that line. So here we've got 1s orbital and we've got 1 electron in our 1s orbital. Okay, and electrons are labeled by an arrow. Okay, a little small arrow. And normally I'll even label my electrons like this. Okay, without double-siding that arrow, usually with just one little half of it. All right, so we've got 1 electron, and it's got to be, you've got to choose a spin state for it. Do you remember how we talked about our quantum numbers and their spin states? If we have paired electrons, they have to have opposite spin states. So I always start my electrons with a positive spin state, with going in the upward direction. Okay, so I indicate it with 1 electron. That's what this little arrow means. That means I have 1 electron in the 1s orbital. So what element am I talking about here? Hydrogen. Yeah, I only have 1 electron. It's in the 1s orbital. That means I can only be talking about hydrogen. Okay? So now let's look at if we've got an orbital that has 2 electrons in it. So this would be a full orbital. Okay, I'm going to label my orbital underneath. And I've got 2 electrons, so I've got 2 arrows. What do you notice about these arrows? Yeah, they have opposite spin states. One's going up, one's going down. Okay, so I usually draw them kind of with a half arrowhead instead of a full one. That's just because that's how I was taught to do it, but you can do it with a full arrowhead if that makes you feel more comfortable, whatever. But the important thing is that they have opposite spin states. So we don't ever have an orbital. We would never have an orbital that looks like this. And we would never have an orbital that looks like this. Right? These are no good. We've got to have opposite spin states to contain within an orbital. Okay? How we place these electrons into their order and how we place electrons into an orbital is following a rule called Hund's rule. Okay, so go ahead and write down what Hund's rule means. It tells us orbitals of equal energy, so things on the same energy level, things in the same orbital, are each occupied by 1 electron before any orbital is occupied by a second electron. So what Hund's rule is essentially telling us is that we have to fill all of 1s2, 1s orbitals before we move on to filling the 2s orbitals. When we fill the 2p orbitals, we're going to fill them 1 across first, then we're going to go back and put in the second. And that's really important for you as you start to fill these orbitals using Hund's rule. Okay, so the second portion of Hund's rule is that all electrons in singly occupied orbitals must have the same spin state. So as we insert electrons, we insert the positive first, then the negative, all the time, or we insert the negative first, then the positive. You can do it either way. I always go positive, then negative. It doesn't really make a difference in the order that you choose, as long as you are consistent. Okay, so I want you to put these rules down first, and then you'll see them put into play here in just a second, and I think the rules will make more sense as we start putting them into practice. Orbital notation. Okay. First of all, let's look at its electron configuration first. Tell me the electron configuration for nitrogen. Electron configuration, remember, is 1s2, 2s2. The arrows that we're doing are orbital notation, so there's two different things. So for nitrogen's electron configuration, we're going to fill 1s2, 2s2, then 2p what? 2p3. Good. So total nitrogen has how many electrons that we have to account for? 7 electrons. Okay, that we're gonna totally account for. So let's go ahead and draw the orbital notation now for nitrogen. Okay? So we've got 3 orbitals that we need to represent here. The 1s orbitals, the 2s orbitals, and the 2p orbitals. So we're going to draw our blank orbitals first. And we always label them underneath. And why does 2p get 3 different lines? Because it can hold 6 electrons, right? We've got the 2p orbitals can have 6 electrons. Okay, so we've got to have 3 different lines there. So now this is the correct way that we start filling in these electrons. We're going to totally account for 7 electrons, but we have to fill the lowest order first, and then we start filling above. We always have to fill with the same spin state first. So we're going to fill the 1s orbitals first. So I'm going to go positive in the 1s orbital, then I'm going to fill the 1s, and I'm going to go negative. I'll do the same thing for 2s. Positive, then negative. Okay? Now is where it gets now is where we start looking at the rules. We need to fill our 2p orbitals, but we need to fill them singly first before we add a second electron to any orbital. So we're going to go like this: 2p1, 2p2, 2p3. Okay, so how many total electrons do I have in my orbital notation here? Total. I have 7, and that's exactly how many I'm supposed to have. And I end up with 2p, 1, 2, 3, which is exactly what my electron configuration tells me as well. Okay? So let me show you what I'm talking about when we look at incorrect orbital notation here. This is correct, so keep that in mind, but I'm going to show you what it looks like if we did it incorrectly. Okay, first of all, this would be incorrect. Why? Yeah, here we started with a positive spin state first, so we can't switch to a negative spin state first in another. Okay? If you start with a negative, you have to do it consistently through the whole time. So start with a negative, then a positive. Okay, does that make sense? I don't know who asked that question. Okay, start with a negative, then a positive. What about this? Why is this incorrect? Yeah, we can't have 2 electrons in an orbital if we've got an empty orbital. We have to fill them singly first, then we can start to double them up. So we'll go back to our correct version here. 2p1, 2, and 3. Okay? Pretty simple. Let's try some more. Orbital notation for the following elements. Remember, orbital notation is arrows. Electron configuration is 1s2, 2s2, 3s, whatever, okay? Let's do boron together, and then we'll do a couple by yourself. So boron is in what group of orbitals? 2p, right? It's in the second energy level, and it's in the p orbital, so it's a 2p orbital. And how many total electrons should we be representing here? We need 5 total electrons, okay? So we fill the 1s orbitals, we fill the 2s orbitals, and we should have 2p, 1. Okay? Let me show you something else. This is also incorrect. Okay, we cannot leave off those 2 empty p orbitals just because they don't hold electrons, right? We have to show that they're empty. So we have to include them in that drawing or in that diagram. We don't have to go on and say 3s, yeah, those are empty. We don't have to go on and say 3p, those are empty. We don't have to continue any farther than that. We need to show the last orbital that contains an electron. Okay, so 2p is the last orbital that contains an electron. So we're going to make sure we include that, and we're going to include every section of that orbital. So x and y. All right. I want you to draw your orbital notation for fluorine.
For fluorine?
For fluorine.
Oh, God.
Perfect. It's really important that when Andy was doing this, he filled his p orbitals, p1, 2, 3, and then he came back to do 4 and 5. I know that it's easy for you to think, okay, I have 5, so I can go ahead and do 1, 2, 3, 4, 5. I want you to get into a habit of going all the way across, then coming back and doing your negatives. Okay, go 1, 2, 3, then you come back to fill 4 and 5. Very good job. Okay, any questions on that? Yeah. Okay, let's try Grace. Let's go with this one. Try neon. Neon should have how many total electrons? 10. Thank you, ma'am. 10. Good. And we have 10 there. 2, 4, 6, 8, 10. Very good. All right. Let's try one a little bit more complex here. I want you to do, let's try nickel. All right. I want you to try nickel next on your own. Go ahead and start putting this up on the board for us. So this is our orbital notation for nickel. Tell me what orbital group is nickel in?
3D.
3D, right? It's in the 3D orbitals. How many total electrons could the d orbitals hold? 10. Good. So we need 5 lines. Perfect. Good. I like that we're filling all the way across first. Then you're going back and filling in your negatives. Perfect. Very good.